Jai Hind students. Till now in satellite communication subject, we studied about various things in which first of all we study about the basics of satellite communication, then we go towards the satellite types, their orbits, their application, all that. After that, our main concern is about to locate the satellite into the space. For that, we derive the various orbital equipment by using the second order differential equation and also establish the link equation for that. Then the next part came into the picture, and that is basically related to satellite link design. Actually, when we are talking about satellite link design, then to design a satellite system, we have to create ground segment and the space segment. Ground segment basically consists of Earth station with various data producer and data sending units, whether the space station segment is related to the satellite itself. When we are talking about this satellite link design, actually we are creating a establishment between the satellite Earth station and the satellite. And during the designing of these satellite and Earth station, we have to derive various equations and the values of various parameters. In the same segment, the main concern is always about the noise, because you know that in the communication part, whenever your signal transmitted from the transmitter side and it travel from the channels, noise will be introduced. So noise is always going to play an important role in the designing of any communication system, and same as that, satellite is also facing the noise problems, because in the satellite communication, signal is going through the atmosphere towards the space, and the various layers of the atmosphere plays a very important role in the designing of the satellite link design. In that series, first of all, we derive the satellite link equation. After that, we go through the various discussion on the satellite system temperature, satellite noise temperature. Actually, as per the definition of noise, any unwanted signal which create any type of disturbance in the normal communication is known as noise. So there are various kind of noise such as external noise, internal noise, as I told you in the previous lectures. One of them is thermal noise, and thermal noise is basically came into the picture due to the resistive component of the system. If you are using a resistance in a particular circuit or any internal component which is offering some kind of resistance in the normal propagation of the signal, then it will create a noise due to the resistive component. So we have to find out the noise temperature, because whenever thermal noise will came into the picture, actually the temperature of that device will increase. That is called noise temperature. And then the next calculation, that noise system noise temperature, we already discussed in the previous one. Now, to understand the performance of any receiver or any system, we use a specific parameter that is called noise. Actually, this noise figure came from the equation, that is input SNR ratio upon output SNR ratio. You are taking a receiver. This is your receiver. This is the input. This is the output. Means for this receiver, on this input side, you have a signal which power is S, and associated noise with this input signal is N, its power is N. So the ratio of signal to noise ratio at input side is called SNR ratio of input. Similarly, we can calculate SNR ratio at output. And by taking the ratio of input SNR ratio with the output SNR ratio, we will get this noise figure. And as you can see that in the SNR ratio, it will always be high, because if SNR ratio is high, means signal power is high and noise power is low. Similarly, SNR out means when we are talking about high SNR ratio at output side, means noise figure will be 1 or less than 1. So it means when we are talking about the noise figure value, it should always be 1 or less than 1. So noise figure is frequently used to specify the noise generated within a device, and the operational noise figure is defined by the following formula. So that noise figure, somehow we are going to relate with the noise temperature we already derived in the previous discussion. So that noise temperature is more useful in satellite communication system, as it is best to convert noise figure to noise temperature Tn, and that relationship came from the Tn is equal to T naught Nf minus 1 Kelvin. So where the noise figure is a linear ratio, not in decibel, and where T naught is the reference temperature used to calculate the standard noise figure at usually 290 Kelvin. So that formula is quite important, because in your examination, sometimes in AKTU, 2 marks question came into the university question paper or your PUTs, that you have given the NF value, you have the T naught value, and you have to find out the system noise temperature Tn. So that is quite easy, but you always understand one point, that this calculation is in the Kelvin, and if you are having some value in the degree, you should convert that degree value in the Kelvin first to solve the numerical. So after taking this noise figure and noise temperature calculation, we are going to find out the G by T ratio for the earth station. Actually, G by T ratio, when we are talking about the G by T, actually T stand for the temperature and G stand for the gain. Gain to temperature ratio is always very helpful for the earth station designing in term of the CNR, because for the earth station, carrier to noise ratio going to play a very important role, and as per the C by N ratio that we derived in the previous section, that is C by N is equal to PTGT-GR upon KTS-BN with the lambda upon 4 pi r whole square, where PTGT is the EIRP, as I told you earlier, externally equivalent isotropically radiated power, where Bn is the bandwidth, K is the Boltzmann constant, and the GR is the gain of the receiver. So you can easily understand by this derivation that carrier to noise ratio is directly proportional to GR by TS, where TS is the system temperature and GR is the gain of the receiver. So in term of the square bracket are all constant, because these all are the constants for a given satellite system. That's why the ratio GRTS, which is usually quoted as simply G by T ratio in decibel with unit dBk-1, can be used to specify the quality of a receiving earth station or a satellite receiving system. So since increasing G by RT, increasing the received CNR. So this is showing the relationship between the G by T ratio with the CN, that if G by T ratio is increasing, then the CNR ratio will also increase, received CNR ratio. So satellite terminal may be quoted as having a negative G by T which is below 0 to 1. This simply means that the numerical value of GR, means the gain of the receiver, is smaller than the numerical value of the TS. So this G by T ratio is the final equation for designing of the earth station. That is directly going to relate the carrier to noise ratio with the gain and the system temperature. So as per our this discussion, you easily understand one point, that your mostly numericals which are came into the university examples are on the G by T ratio or the EIRP and the loss equation, that was the satellite link equation, that all are going to be used for the numerical problem. So now we take some specific numerical problem which comprise all these, comprise use of all these equations, and we should understand that. So our first numerical is, an earth station has a diameter of 30 meter, means this 30 meter is related to the antenna of the earth station. So 30 meter with an aperture efficiency of 68%, means neta A. Then it is used to receive a signal at 4150 megahertz. At this frequency, the system noise temperature is 60 K when the antenna point at the satellite at an elevation angle of 28 degree. These are the given values, means neta A is the 30 meter, aperture efficiency is 68%, and the frequency is 4150 megahertz. And the received signal and the system noise temperature for this is 60 Kelvin with the elevation angle of 28 degree. These are the inputs. So what is the earth station G by T ratio under these conditions? Then the next part of this numerical is, if heavy rains causes the sky temperature to increase so that the system noise temperature rises from 88, means 60 Kelvin to 88 Kelvin, what is the new G by T ratio? Means you have to find out the G by T ratio and all the other values are given. So how you are going to do that? As you have the neta A, first of all you have to calculate the receiver gain. So when we are talking about the receiver gain, GR is equal to neta A 4 pi A upon lambda square. This is the formula which can be derived also as neta A pi d upon lambda whole square by using that diameter part with this comparison. So at we given that 4150 megahertz, lambda you have to calculate, means F is equal to C by lambda. So by this formula you can calculate the lambda from this 4150. So for 510 megahertz frequency we will get the lambda is wavelength is equal to 0.0723 meter. So put these values in the equation. D is already given as 30 meter because you can see that is 30 meter. So you don't have to convert this. Put this value, solve this, then we will get this value, that is 1.16 into 10 to the power 6 or 60.6 dB. That is in the dB. That is the normal, that value that is in dB. And for converting this into the dB, you use this formula 10 log 10 the value. Now converting the TS into the dPK, decibel per Kelvin, decibel Kelvin. So you have the formula TS is equal to 10 log 10 60 because the value is 60 Kelvin, that is in the normal Kelvin, but you have to convert it into dBK. So 10 log 10 60 is equal to 17.8 dBK, means G by T ratio is equal to 60.6 minus 17.8, that is 42.8 dBK. That is the answer. So then again new problem is here. They are saying that this is the answer of this first part. But when you are talking about this heavy rain condition, now system temperature will convert to 88 Kelvin. So first of all you have to convert this 88 Kelvin into by using this formula in dBK. You will get the value 19.4. So by dividing 60, subtracting 60.6 minus 19.4, you will get this 41.2 dBK. This is a very important numerical which came into the previous university examination. So you have to know that these all small formula with the diameter and all problems you can use for this. Then the next numerical, which is also very important because this satellite equation in dBW is used very vast in this equation. So what is our numerical? A satellite at a distance of 40,000 km from a point on the Earth's surface radiated a power of 10 watt from an antenna with a gain of 17 dB in the direction of the observer. Means that is all about the direction of the observer, and the related points are 40,000 km above the Earth surface, and all other values are there. So find the flux density at the receiving point and the power received by an earth station antenna at this point with an effective area of 10 meters square. So which kind of formula you are going to use here? You can easily find out that you have PR is equal to EIRP plus GR minus LP, that is loss, where ERIP is equal to PTGT when we are going to convert it into dB. So because basically it is in the watt, but when you are converting in decibel watt. So similarly gain, that is in normal dB, you are going to convert it into this one, and because G is equal to, that is the formula as per the AE upon lambda square, that is the formula for the G. Then path loss is given by the 20 log 10 4 pi upon, that is also the value. So these all formula is going to use for this formula. How? See, you know that flux density formula is F is equal to PGGT upon 4 pi r square. P value is 10, 50, 4 pi 4 into 10 to the power 7, 10 square. That is the answer for the flux density. So by using because this is equal to PTGT EIRP, and flux is by using this upon 4 pi r square. So from where this r is coming, you can see that effective aperture of area aperture of 10 meters square. So you can solve this. This is here. Okay. Now the power received with an effective collecting area of 10 meters square is therefore PR is equal to 2.49 into 10 to the power minus 13. So the calculation is more easily handled using decibel, noting that 10 log 10 4 pi is equal to 11 dB around. So F in dB, when you are going to calculate, that is the answer. Because when you apply the logarithmic here, PTGT are in the multiplication, so that log A plus log B, and another is log A by B ka formula use kare. So F in dB is minus 136.0. So then you can see that F is equal to F dB meter, then PR is equal to minus 136 from here plus 10, then that is the answer, 126 dBW or minus 96 dBm. So here we put the antenna efficiency aperture into decibel greater than the 1 meter square, and also given the answer in dBW and dB decibel above 1 watt and 1 milliwatt. So this is also a problem. So another numerical again you can find out, so that a satellite is in the previous exam, means we are using that same points here again. We are just solving this numerical to find out a specific condition. So you can see that in the satellite is in the previous example operate at a frequency of 11 gigahertz and the receiving antenna gain is 52.3. Find the received power at the earth station in dBW and the dBm. It is common practice to quote transmit power dBW and received power in dBm. So that is the formula. ERIP is already we can find out in the previous one. You can see here 27. So by this formula. So then this one GR is equal to 52.3. So path loss LP is equal to this. So by putting all these values in this equation, you can say 27, 52, 250.3, you will get this minus 126 dBW. So the received power in dBm unit is numerically 30 dB greater than the dBW. W. So in the same case for the second part, you can see that path loss, these are the here, these all values are the here, but PR is equal to 126 plus 30, that is minus 96. So you can see here in the previous example the value is also minus 96. Now we have the same answer because the figure of 52.3 dB is the gain of the 10 meter scratcher of the 11 gigahertz, means the antenna aperture is the same in the both cases. So that is about the numerical problems. Now after all these, we are going to concentrate on the satellite earth station. And when we are talking about the satellite earth station, that is basically divided into three types: a transmitting type, receiving type, and transmit receiving type. Means first of all, they are using only for the transmission purpose, another one are only for the receiving purpose, or third one is the both combination of transmission and receiving. So when we discuss the satellite have various subsystems such as communication system, subsystem, TTCM, AOCS, power supplies, and other one. Similarly, earth station are also having some general subsystems, and that are antenna, generally reflector type, feed system, and the tracking equipments. So these are the satellite earth station basic factor on which station design depends. These factors are which type of service you are going to use, designing of the transmitter, designing of the receiver, function of that specific station, means that is going to use for the transmission or for the receiving. Similarly, the characteristics of an antenna, the antenna which is going to use for there, because sometimes you are going to use the same antenna for transmission and the receiver in duplex mode. Similarly, the frequency band of operation, that one is the most important, because first of all you have to find out the frequency band for which you are going to design that satellite earth station. So this is the diagram of a basic satellite earth station, and you can see that this is the terrestrial network which is going to be directly connected through the antenna, and that is connected with the baseband equipment. This baseband equipment are basically having antennas, that is parabolic reflector antenna are mostly used. So this upper part is showing the basically you my mistake, I am just giving you the wrong example. This is the terrestrial network. This is the terrestrial network. When we are talking about the terrestrial network, actually the terrestrial network is the lower part from where you are going to collect the data which is going to be transmitted, or terrestrial network is the part which is going to take the information from the outer space. So that is part is another. So our antenna is basically here. This is the antenna which is receiving the signals from the space or sending the. If it is a transmitting earth station, means it is getting the data from high power amplifier, up converter, modulator, and encoder. If it is a receiving type, then the basically the another part is going to use. So these all designing are as per the previous one, the low noise amplifier, use of high power amplifiers, that are all required for the basic functioning. So encoding, decoding are also the important part of the satellite earth station. So by this lecture, we conclude the complete satellite link design and the satellite earth station designing, and we discussed the various parameters and the factor which are responsible for the designing of a satellite earth station. So in the next lecture, we are going to describe the another aspect of the satellite communication. So till then, thank you.